Today we'll talk about log functions and their models. I don't know if you recall from Algebra 2 or not, but a logarithm is a way to find the exponent on a given base. So that is the purpose of logarithms, to find an exponent of a base. It allows us to write numbers in different bases. So by definition, it is log base b of y equals x, where b is your base, y is your value, and x is your exponent. So if I take this log, I can rewrite it in exponential form. My base was b to the exponent x equals y. So it is b to the x equals y. So let's look at one that is written. We have log base 2 of 8 equals 3. Base is 2. 3 is the exponent. And 8 is the value. So it is 2 cubed equals 8. There are two special logs. The first is called common log, and its base is 10. I want you to notice how common log is written. It is log x. There is no base there. Just like when we would write x equals 4, it is understood that there is a 1 in front of the x without us writing it. Well, when it's log and there's no log there, we understand that base to be 10. So you can write a little 10 in there. So then if I rewrote it in exponential, it becomes 10 to the k equals x. Our second special log is called natural log. Its base is e. Notice how it's written. Ln x. Ln. Notice there is no base there either, but it is ln, ln x. That means its base is e, so put a little e in there. So it is e to the k equals x. All right, let's try a few common logs. Log 1 equals x. So 10 to the x equals 1. Well, to get a value of 1, my exponent must be 0. Because anything to the 0 is 1. Okay, let's try log of 1/10,000th. I don't know what it equals, so we go equals x. So that means my base is 10. 10 to the x equals 1/10,000th. So that means 10 to the x equals 1 over 10 to the 1, 2, 3, 4, which means it is 10 to the negative 4 because I want this to come up to the numerator, so I need negative power. So x is negative 4. Okay, log of a negative 3. No base, so its base is 10. We're going to say equals x. So 10 to the x equals negative 3. Can you ever get negative value? No. Yesterday we learned all logs or exponentials approach 0. They just never cross over 0. They never go negative. Never negative. So this is not possible. No solution. Never negative value on a log. All right, and the last one, log of the cube root of 10 equals x. So that base is 10. So 10 to the x equals the cube root of 10. Well, the cube root of 10 is the power 1/3. So x equals 1/3. All right, these are rewrites. So first we're going to take the log and rewrite it in exponential. So my base is 3, my exponent is 2, and it equals my value of 9. 3 squared equals 9. Does it? Yes, it does. Let's try B. Base is 8, power is 0, equals value of 1. 8 to the 0 equals 1. And the last one, base is 5, exponent is -2, equals value of 1/25. 5 to the -2 equals 1/25. And yes, it does, because remember, 5 to the -2 means 1 over 5 squared, which is 1 over 25. So that is correct exponential form. Now let's go the other way. Given the exponential, rewrite it in log. So I need log. What's my base? 6, 2, or 36? 6 is my base. Log base 6. Of the value, my value is 36, equals the exponent. Well, my exponent was 2. So log base 6 of 36 equals 2. Okay, let's try the next one. Log base. My base is 5. Of the value, my value is 125, equals the exponent. My exponent is 3. Log base 5 of 125 equals 3. All right. Remember, when you are evaluating logs, rewrite them in exponential form with the x as your exponent. Then you want your equations to get the same base. And your exponents will then be equal. So let's take this first one. Log 4 of 64. We're just going to say we don't know what it equals, so we equal it to x. And we're going to do the rewrite. 4 to the x equals 64. So I need to rewrite 64 in base 4. So that's 4 to the x equals 4 cubed. That means x equals -3. Excuse me, +3. So log 464 equals 3. Okay, let's do the next one. I don't know what it equals. So 2 to the x equals 0.125. I need to write this as base 2. So 2 to the x equals 125 over 3 decimals would be 1,000. If I divide both of these by 25, I get 5 over 40, which still divide by 8, or excuse me, divide by 5, gives me 2 to the x equals 1/8. Well, that's 1 over 2 cubed, which brings it's 2 to the -3, because I got to bring it up. So x is a -3. Let's try the next one. 1/4 to the x equals 256. Well, notice on these previous ones, my base was not fractional. It was always a whole number. So how can we change 1/4 to a whole number. It would be 4 to the negative 1. That would flip it to the top. Then I still have that x, so it's 4 to the negative 1x. Now I must rewrite 256 as base 4. So 256 is 4 to the 4th. So that means negative x equals 4, which means positive x must be negative 4. And then the last one here, I don't know what it equals, so 32 to the x equals 2. Do you also notice that in any of these, we always wrote them in the smaller base, not the larger base? So which is the smaller base here, 32 or 2? 2 is. So I need to rewrite 32 is base 2. 32 is 2 to the 5th, and I still have that power of x, equals 2, which is 2 to the 1. So this means that 5x equals 1. Divide by 5, x is 1/5. All right, we have a few more here. This is already equal. Base 4 to the power 3 equals the value x. 4 cubed equals x. Well, 4 cubed is 64. So x is 64. Next one. 4 to the x equals 4 to the negative 2.3. So x is negative 2.3. Well, this one, 4 log base 4. When you have the same base as you have the log base, since logs find exponents, and my exponent is a log to the base, those should just reduce out. So log 4 raised to the log 4 reduces out, and you're left with an exponent of 3. Just to show you that logs and exponents are inverses of each other. If they're inverses, they reflect over the line y equals x, which is right here. Here's y equals 10 to the x. Here's y equals log 10 to the x. Notice how these are true reflections over y equals x. So that means that they are the inverse of each other. That is why logs find exponents. So the inverse to e to the x would be ln x. So why we do this is because when we can't get the bases to be the same, we can log both sides. Then my bases will be the same. Like on these problems. Can you ever get 2 and 72 to be base 2? Let's see, 2 to the 5th is 32, 2 to the 6th is 64, 2 to the 7th is 128. I didn't hear 72 in there. So no, I cannot get 72 to be a base 2. So then we need to log both sides. Now we can do this a couple of ways. If we would log base 2, this would reduce out. So if I log base 2 on this side, I must log base 2 on the other side. So log 2 reduces. So I have my x equals log base 2 of 72. And then I put that in my calculator. So if you're putting it in your calculator, you can do alpha window, and you see number 5 there says log base. Press that, and it is log base 2 of 72, and you should be able to fill that in. And we usually go to 4 decimals, so we get about 6.1699. I need to see both of these. This was the algebra, that is the estimation. Now, the other way we could do this is you can log base anything. So we had 2 to the x equaled 72. So say I chose to common log both sides, because then I'd be rewriting them both as base 10. So this would be log, log. Well, as we learned, exponents move to the front. So I have x times log base 2 equals log 72. I'm going to divide by log base 2. So x equals log 72 divided by log 2, which also gives me 6.169, because this is what's programmed into that log base button. All right, let's try another one. E to the negative x equals 3. Can you ever get 3 to be base e? So it'll be no. So we're going to natural log both sides. So again, this reduces, and I have negative x equals ln 3. Well, I want positive x. So I would have x equals the negative of ln 3. And there's my algebra. So I come to my calculator and press negative ln 3. And I get negative 1.0986. All right, solve the next one. First we divide by 2, and I get 10 to the x equals 33. Can I get 33 to be a base 10? No, so I need to log both sides. So log 10 reduces, so I have x equals log 33. I go to my calculator, because now my algebra is done. Log 33 is about 1.5185. All right, and the next one, subtract 5. 2 times 3 to the negative 2x equals 162. Divide by 2. 3 to the negative 2x equals 81. Can you write 81 as base 3? Yes, you can. So I must write it as base 3. That is 3 to the 4th. So negative 2x equals 4. So x equals negative 2. So in your problems, they're not going to be divided out when you should log and when you should use exponent. You will only log if you cannot write them as the same base. But if you can write them as the same base, you must write them in exponential. Let's try the next one. It is in logarithmic, so I'm just going to still do my rewrite. 2 to the 1.2 equals x. Well, I don't know what that is, so I go to my calculator. 2 raised to the 1.2, and I get 2.2974 is approximately what x is. Next one, ln x equals 2. Well, my base is e, so e squared equals x. Well, e squared is about 7.3891. All right. If you are finding the domain of a log function, remember that the value must always be positive. So that means the value must be greater than 0. That's how we write must be positive. So in this equation, y equals log of x plus 3. X plus 3 is my value. So my value must be positive. So x plus 3 is greater than 0. So I'm going to solve that for x. And I get x has to be greater than a negative 3 as my domain. Likewise in the next one. My value is square root of 3 minus x, then minus 1. So square root of 3 minus x minus 1 must be positive, greater than 0. Add 1. Square root of 3 minus x must be greater than 1. Square both sides. 3 minus x must be greater than 1. Subtract 3. Negative x must be greater than negative 2. Divide by negative 1. X must be less than 2. All right, and then this last problem. Decibels can be computed by d of x equals 10 times log 10 to the 16th times x. Find the sound density when x is 10 to the negative 5. So this is 10 log of 10 to the 16th times 10 to the negative 5, because I replace 10 to the negative 5 into this x spot. So that is 10 log 10 to the, when you multiply, you add your powers, 11th. So this 11 multiplies to the front, so I have 11 times 10 log 10. Well, log 10 reduces out, so I have 11 times 10, which is 110 decibels.